Hi, my name is Chen. I'm excited to present our work, Birth and Death of a Rose. The paper is in collaboration with Yunji, Elliott, and Jiajun from Stanford University. Let's first watch a short video. It captures a dynamic scene of a backyard bush with several roses. The roses begin as tadpoles. They open their petals and bloom into full glory. Then, one by one, the roses wither and fade, completing the cycle of their brief but beautiful lives. Such dynamic phenomena are very common in the physical world. Beyond the birth and death of a rose, other similar phenomena include the burning of candles, the melting of ice cream, the sprouting of young plants, and the baking of bread. What you just saw are not real, they are all fictional scenes, rendered using a graphics system. To understand how they were made, we need to look beyond the form and decompose them into different components. We use the scene of the birth and death of a rose as an example. First, we used an environment map of a sunny backyard to set the lighting of the scene. Then, we collected some static assets, like the bush here, to interact with the roses. Well, those assets are easy to find online. Creating the blooming of a rose is a different story. To represent that kind of transformation, we need a dynamic 4D asset, something that can grow and shrink over time. This is the focus of this paper. As we just said, modeling these dynamic objects are not a trivial task. In traditional computer graphics, we don't have standard practice to create such assets. Similarly, for this candle burning scene, we need to create candles that gradually shorten. For this ice cream melting scene, we need to create ice cream that gradually loses its volume. How can we create these dynamic assets? A direct idea would be just modeling how the RGB appearance of a rose will change throughout its lifespan. However, if we look closer at the evolving rose, we can realize that it is not the superficial RGB rendering of the rose that is changing over time. The true underlying properties that change are its geometry, albedo, and material. We collectively call these evolving properties temporal object intrinsics. These intrinsic properties can interact with different extrinsic conditions to produce different appearances. In this paper, we focus on the challenging task of automatically creating those evolving object properties for different natural phenomena, namely temporal object intrinsics. We aim for a generic data-driven pipeline that is not tailored to a specific type of dynamic motion. Our approach can help create these dynamic assets for various similar natural phenomena, such as rose blooming, bread baking, and plant sprouting. This is a task that, to the best of our knowledge, has not been explored in previous literature. Why? The 4D data for the supervised learning of this task is extremely rare. For example, if you search for a blooming rose in a large database of 3D models, it will return no results at all. Despite the lack of 4D supervision data, the internet contains abundant 2D knowledge on object dynamics. If searching for a rose blooming time-lapse, Google will return nearly 1 million results on this. Moreover, this large amount of 2D data has been used to pre-train foundation models, like image diffusion models, video diffusion models, and pre-trained feature extractors. That provides an interface to access this data. Given these foundation models, is it possible to find a data-driven pipeline that distills temporal object intrinsics from those foundation models? We are inspired by an awesome prior work called score decision sampling, or SDS. It distills information from foundation models to the 3D content. Specifically, SDS works by optimizing a 3D neural field using guidance from 2D diffusion models. SDS has a notorious problem called the Janus problem. It refers to the view inconsistency issue when doing score distillation. As SDS uses 2D to distill 3D, it lacks 3D knowledge, resulting in inconsistent views in the generated 3D content. For example, here, if we try to obtain a 3D dog with SDS, we have a pre-trained diffusion model with the dog as a prompt. During the optimization, let's say at 2 optimization iterations, we sample 2 different views. At 2 different optimization timestamps, the diffusion model considers the 2 renderings independently. It lacks 3D knowledge and cannot tell whether this view should contain a head or not. So back projecting to 3D, it will generate a 3D content with 2 heads. This gives a 3D rendering with significant artifacts, as on the right. Remember that in this project, our goal is to create 4D content. In this scenario, the inconsistency issue extends from view inconsistency to temporal inconsistency. This is because the diffusion models not only don't know about 3D, but they also don't know about time. Let's say we wish to distill a 4D content with the prompt rose blooming. We initialize a 4D field with n timestamps. We sample several different timestamps. And finally, we try to let the diffusion model give guidance to the rendered dynamic frames. In this way, the diffusion model cannot tell whether the rendering should be depicting the blooming state of a rose or a closed bud of a rose. Therefore, it gives the most probable result to each of the sampled frames, resulting in static 4D assets. As shown on the right, if we use vanilla SDS to generate 4D assets, it will give you almost static 4D assets. How to solve this problem? Intuitively, we need to let the diffusion model become aware of 4D information. To achieve this goal, for each natural phenomenon, we create an intermediate 4D representation. It implicitly contains information on viewpoint and timestamps. We call this representation a neural template because it defines a unified 4D semantic evolution of a natural process, and we will formally define and discuss later in this talk. Now, with the created neural template representation, we can use it to condition the diffusion distribution. With the neural template control, now the diffusion distribution becomes conditional and therefore is temporally aware. Therefore, for sample time frames, it can give the correct stage and viewpoint of the desired 2D rendering, which results in a correct 4D content. Now we discuss the structure of neural template. Formally, neural template is a mapping that takes input as the viewpoint and timestamp used in the rendering of SDS and outputs an implicit semantic feature map containing 4D semantic information. For each natural phenomenon, we build a neural template to encode the 4D semantic information. We refer our audience to our paper for more details. With the help of a neural template, we can finally use score distillation to generate 4D temporal object intrinsics. Now we describe the complete pipeline of doing so. Given a 4D field, we follow the framework of SDS by randomly sampling a timestamp and a viewpoint. In this way, we can obtain the rendered temporal object intrinsics, including the 2D maps of normal, albedo, and material parameters. We use a physically based renderer to obtain the RDB rendered images. Then we should use a diffusion model to provide guidance to the rendered image. We use the same viewpoint and timestamp as rendering to condition the neural template to get a feature map, and we use this map to condition the diffusion model. The controlled model will give you a score, specifically with information about the viewpoint and timestamp to update the 4D field. After the convergence of field optimization, we can obtain a 4D field describing the natural phenomenon. We refer the audience to our paper for more details. Now, we describe applications of this task and framework. Using the generated temporal object intrinsics, we can insert them into any 3D scene, render them from any viewpoint, under any environmental lighting conditions, at any time of their lifespan. As in this previous video, we can generate a scene of rose blooming and withering. Similarly, we can observe how bread is baked from fresh dough on a tree in your bedroom. Compared to other visual generation techniques like video generation models, with this approach, we can freely control the layout, camera, and lighting. We can also witness how young plants are sprouting in a flower pot. We can move the flower pot into a cave to see how it will respond to the lighting conditions. Again, all with full controllability. More examples can be found in our website. How would the proposed method compare against prior works? To the best of our knowledge, there are no baselines doing exactly the same task, so we compare with baselines on similar tasks. We first compare our model with state-of-the-art methods in 4D generation. In the area of 4D generation, most methods directly generate 4D objects with baked-in appearance, making them not directly usable to compose a dynamic scene of varying lighting conditions. 4D-FY is a signature method in this task. We compare our method against 4D-FY on different phenomena. For example, blooming of a rose, melting of ice cream, sprouting plants, and several other phenomena. We can see that our method generates better dynamic evolution on object geometry, while 4D-FY relies on vanilla SDS without conditioning, making them hard to represent significant geometry and material changes. Therefore, it generates mostly static assets. Moreover, our model can be used in relighting and scene composition. We then compare another task that potentially generates 4D content, 4D reconstruction. A 4D reconstruction method takes a video as input and does reconstruction using pre-trained 3D reconstruction models. Stack 4D is a representative work in this area. We also compare our method to Stack 4D on rose blooming, ice cream melting, and plant sprouting, and several other phenomena. Despite generating significant geometry changes, the novel view rendering quality at views other than the input view is typically inferior due to the lack of training data coverage in the 3D lifting network. Our method, however, uses guidance from a 4D neural template and information from 2D diffusion models to obtain 4D contents that exhibit natural dynamics and 3D geometry. Similarly, the 4D model generated by Stack 4D cannot be used in relighting or scene composition. For more comparisons, please refer to our paper. So, in conclusion, in this project, we propose a new task to explore, generating temporal object intrinsics for natural phenomena. We propose a new intermediate repetition neural template to represent the 4D semantic changes in the dynamic process. Finally, we propose and test a new framework to accomplish this task. For more results, please check our website and our paper. Thank you for your attention.